Topic of this video is parametric design for climate-responsive architecture, planning tools and practices. The contents of the training are parametric design and goals, key tools and software, workflow structure for rhino plus grasshopper, ladybug plus honeybee, parametric urban design for sun exposure and adaptive form, urban zoning and morphology based on solar access, envelope optimization, optimization objectives, long-term climate adaptability, summary and reflections. The learning objectives of the training are: apply parametric workflows to climate-responsive architecture, explore software platforms, plugins, and data pipelines, integrate performance goals with iterative design processes. Parametric design is an approach that uses algorithmic thinking to solve design problems by translating the relationships between internal and external variables into formal parameters. This design process utilizes parameterized digital models where changing an input value automatically updates the geometry and lifecycle scenarios, generating responsive architectural forms that are intrinsically constrained by defining equations and multi-step algorithms. As a result, shapes and systems adapt based on site, climate, or performance targets, allowing designers to link real-world variables, such as climate conditions, energy demand, and structural behavior, into the model to efficiently find solutions. This approach allows for iterative optimization and rule-based geometry. The design proceeds through cycles of generating alternatives, divergence, and evaluating them against objectives, convergence, until constraints are met, often using generative optimization algorithms, like SPIA2 or NSGA2, to search for the best combination of solutions across multiple performance indicators, e.g., energy, cost, and comfort. The primary goals of applying parametric design to climate-responsive architecture revolve around achieving energy efficiency and environmental friendliness by streamlining complex design and evaluation processes. Parametric modeling enables architects to overcome the time-consuming challenge of evaluating energy performance in early design stages by dynamically controlling geometry to evaluate a large number of alternative solutions quickly and efficiently. This methodology supports performance-based generative design, where climate and environmental criteria, such as sunlight and thermal comfort, are used as design restrictions that actively drive the generation of the building's form, geometry, and materials. Ultimately, the aim is to create intelligent designs, such as responsive kinetic envelopes, that interactively manage natural energy sources like solar radiation and wind. By optimizing these passive strategies, designers can reduce reliance on mechanical HVAC systems, contributing to long-term sustainability and the significant reduction of the structure's environmental impact and $CO_2 emissions. There are lots of software and tools for parametric design, but the most common used software will be explained here. Three main categories are created to differentiate their functions and workflow: Rhino plus Grasshopper, Ladybug plus Honeybee, Climate Studio plus Design Builder. The workflow begins by defining both the climate context and the geometric variables that control the building form and envelope. To ensure climate responsiveness, the system must ingest comprehensive climate data, typically from standard sources like EPW, typical meteorological year, weather files. This data is essential for accurate thermal and energy performance predictions. Then the parametric model defines the elements that the designer can manipulate to respond to the climate. These elements are treated as variables or parameters like form and orientation and envelope properties, openings and shading. Parametric modeling systems utilize logic trees or algorithms to define relationships between these parameters and the generated geometry. Changes to a simple parameter, like span or window size, automatically update the entire complex model, enabling designers to evaluate numerous design alternatives rapidly. For a design to be climate responsive, the geometric model must be dynamically linked to performance simulation software. This is where tools functionally similar to Design Builder or Climate Studio integrate with the parametric design environment. Two types of evaluation can be conducted: real-time performance evaluation. Simulation plugins connect the variable geometric model, e.g., created in Rhino, Grasshopper, to established energy simulation engines like Energy Plus, or daylighting engines like Radiance. This allows for the real-time evaluation of how changes in parameters affect performance metrics. Targeted performance metrics. The performance metrics that drive climate-responsive design include energy balance, thermal analysis, life cycle assessment, LCA. The ultimate application of parametric workflows is using optimization algorithms to guide the generation of solutions that are optimally balanced against multiple, sometimes conflicting, climate-related objectives. To achieve this performance-driven generative design, transcoding environmental parameters, designing for future climate scenarios, cost and carbon optimization are ways to follow. By leveraging these integrated parametric and simulation capabilities, designers can ensure their building components and overall forms are generated and justified by their ability to maintain energy efficiency and environmental performance, even as external conditions, such as climate, evolve over time. Parametric workflows using Rhinoceros and Grasshopper offer a robust methodology for integrating climate-responsive strategies into architectural design by automating geometry generation, embedding design rules, performing real-time performance evaluations, and linking environmental data to BIM models. One major application is the assessment of embodied environmental impact through lifecycle assessment, LCA. Grasshopper enables designers to generate numerous structural alternatives using adjustable parameters such as span and frame spacing, while embedding structural rules of thumb from standards like the Eurocode. As the model changes, Grasshopper automatically selects appropriate structural profiles and calculates material quantities. These quantities are linked to environmental datasets such as Ecological, allowing instant evaluation of indicators like global warming potential and the identification of high-impact materials, such as concrete. Real-time feedback enables designers to compare variations, such as the effect of larger spans on carbon performance, and make informed decisions during early conceptual stages. Parametric models can also be converted into BIM objects with environmental attributes, ensuring interoperability within open BIM workflows and maintaining climate-responsive data throughout the building lifecycle. Parametric design also enhances climate-adaptive site planning. Rule-based evaluation allows building codes and environmental standards to be encoded into digital tools, while hydrological calculations for rainwater detention ponds can be fully parametrized, including catchment areas, runoff coefficients, rainfall durations, and required detention volumes. This supports accurate stormwater management and reduces flood risk. Additionally, parametric optimization supports passive design strategies such as shading, orientation, ventilation, and daylighting, enabling designers to explore geometric adjustments that respond effectively to site-specific climatic conditions. Ladybug is a Grasshopper plug-in used for visualizing and analyzing atmospheric data related to a building's location and climate. This atmospheric and climatological data is crucial for early-stage conceptual design, which dictates the performance of a building throughout its life cycle. Key applications of Ladybug for climate responsiveness are data visualization and input. Ladybug reads local weather data from standard sources, like the EPD weather file. It then provides visualizations and representations of various climatic factors, which serve as direct inputs for design decisions. Climate analysis and visualization. The tool generates graphical and spatial analyses necessary for climate-responsive strategies, including sun position and trajectory, radiation analysis, psychometric maps, shadow study, wind simulation and wind map, visibility analysis. Performance-driven geometry. By visualizing these factors, Ladybug helps designers optimize building orientation, form, and shading to manage solar heat gain, maximize daylighting, and leverage natural ventilation, all key goals of bioclimatic design. Honeybee is a Grasshopper 3D extension that connects the geometry defined in Rhino to certified simulation models and engines for comprehensive performance evaluation, enabling design to be driven by expected performance rather than resulting from previous decisions. Key applications of Honeybee for climate responsiveness. Building energy modeling, BEM. Honeybee connects to simulation engines like Energy Plus to perform building energy management and comprehensive energy simulation of the model. This allows designers to calculate and optimize energy consumption for heating and cooling, which often requires a high-tech solution if passive strategies fail. Thermal and climate comfort simulation. It connects to simulation engines to evaluate factors related to climate comfort. This is critical for assessing how design choices, such as material thickness, insulation, and shading, influence the interior environment and occupant well-being. Daylight and transparency simulation. Honeybee uses simulation tools like Radiance to assess daylight and transparency simulation. This is vital for achieving high-quality interior lighting without excessive heat gain or glare, which is a major objective of sustainable and performative design. HVAC calibration. The tool supports HVAC calibration by simulating the performance of mechanical systems in conjunction with the building's geometry and passive strategies, ensuring the reduction of energy usage. The Ocean One Pavilion, a highlight of Expo 2012 in South Korea, serves as a premier case study for parametric design applied to natural ventilation strategies. The building's most innovative feature is a 140-meter-long kinetic facade composed of 108 vertical lamellas made from glass fiber reinforced polymer, GFRP. Inspired by the biological paradigm of fish gills, these lamellas are individually controlled via a digital system that enables them to bend asymmetrically when actuated by motors. This precise parametric manipulation creates gill-like openings that are specifically designed to facilitate controlled airflow and optimize air circulation throughout the building's interior. By automating the interaction between the building envelope and environmental inputs, the pavilion functions as an interactive interface that manages natural energy sources like seasonal wind. This performance-based approach ensures the structure remains acclimated, intelligently providing ventilation to reduce the overall energy consumption of mechanical HVAC systems. Ultimately, the pavilion demonstrates how morphological differentiation can transform a static enclosure into a living, breathing skin that responds dynamically to its climatic context. To understand this complex engineering, one can imagine the building's skin as a mechanical set of lungs. Just as lungs expand and contract to regulate oxygen, the pavilion's lamellas flex and open to inhale fresh air and exhale heat, maintaining a constant state of internal comfort. Parametric urban design for sun exposure and adaptive form. Parametric design can be used for urban form studies by translating environmental data directly into geometric differentiation, which is key for shading optimization. Transcoding sun exposure into form. Parametric tools allow performance parameters, such as differential sun exposure or wind loads, to drive geometric design. For instance, a sun exposure map imported from an environmental analysis tool can deliver data input for component differentiation. The parametric designer can set up a dependency rule. The higher the sun exposure of a surface patch, the smaller the opening of the facade component at that location, thus optimizing daylight penetration and minimizing solar gain. The resultant facade articulation becomes a representation of the surface's differential exposure to the sun. Infinity Loop, O Tower, China. The OPPO R&D headquarters, designed by BRK Ingalls Group in Yuhang, China, utilized its distinctive form for self-shading. This is an example of optimizing the architectural massing against external parameters, minimizing energy use and enhancing natural light. The design incorporates adaptive louvers oriented in relation to the sun's location, covering the facade to lower solar gain by up to 52%, significantly reducing cooling load costs and lowering glare. Although the sources refer to a single building, the massing and facade articulation demonstrate how optimization of solar control impacts form. The solar envelope is a concept of solar zoning that defines the volumetric limits for development on a given site that will not cast critical shadows on neighboring properties during designated energy receiving periods of the day and year. This serves as a meta-control on performance at a higher level of abstraction than typical building codes. When applied, the solar envelope forces building form to respond to orientation. Development tends to be lower on the south side of a street than on the north, preserving the major southern exposure. Buildings and streets gain distinct directional identities. Because the envelope is generated by the sloping rays of the sun, the resulting forms are complex, multifaceted crystals or warped surfaces, leading to unique shapes rather than repeating rectilinear designs. Spanish Grid, downtown Los Angeles, high density. A project on the diagonal Spanish Grid achieved high densities, 80 to 100 degrees AC, while ensuring 4 hours of winter sunshine and 8 hours of summer sunshine. The resulting solar envelopes appeared crystal-like, and the resulting designs were typically consistently higher on the south side than on the north. The resulting spaces were light-filled, allowing for distance views and the free flow of air through the city. The curving streets, mid-density example originates from studies testing the feasibility of the solar envelope concept at the urban design scale, specifically for mid-density residential areas. In this application, the solar envelope, a mechanism for solar zoning that defines the volumetric limits for development to guarantee solar access, was generated to run continuously along curving suburban streets. The zoning rules specified that shadow fences dropped only at the front and back property lines, allowing the envelope to flow smoothly along the street front, adapting to the curve and orientation of the street. This approach aimed to increase typical suburban densities, 5 to 7 DU, AC, to a higher mid-density range of 25 to 45 dwelling units per acre, 62 to 111 DU per hectare. The resulting building designs allowed for innovation and diversity, ranging from townhouses and courtyard clusters to apartments, creating variety within a neighborhood while ensuring longer periods of sunshine, 6 hours in winter, 10 hours in summer, than typically provided in high-density grids. Parametric design provides a systematic and iterative methodology for envelope optimization in high-performance buildings by dynamically linking the building's geometry and material composition to quantifiable performance criteria. This approach is crucial because the building envelope dictates energy flows, such as heat loss and gain, daylighting potential, and solar control, which are overwhelmingly determined during the early conceptual design stages. Key envelope parameters subject to optimization include thermal and material properties. Designers can vary and test the influence of the building's attributes on thermal performance, such as the thermophysical characteristics and material thickness of the envelope, walls, roof, windows. This includes optimizing the number of insulation layers, such as extruded polyurethane, which contributes to the wall's R value. Glazing and openings. The parametric model allows for the optimization of the window-to-wall ratio, WWR, size, and dimensions of windows. The objective is to strike a balance that provides sufficient daylighting while maintaining good thermal performance and avoiding excessive solar heat gain. Shading device geometry. For climate responsiveness, optimization can determine the projection length of a fixed overhead shading device. This is critical to ensure the device performs optimally, blocking unwanted solar heat gain during cooling season while permitting beneficial solar gains during heating season to reduce energy use. Overall form and surface area. Parametric design can be used to optimize the overall architectural massing and envelope form. For example, the use of parametrically defined curved shapes can significantly reduce the area of the exterior surface, thereby lowering both the heat energy gained from the outside and the heat lost through the envelope. Parametric optimization allows high-performance buildings to be evaluated against specific, measurable goals beyond simple energy consumption, energy balance, and performance. The core objective is to find the best performing solutions for a favorable energy balance, typically by linking the geometry to thermal analysis tools and minimizing cooling and heating loads. Cost optimization. The model can be structured to find the solution that results in the least overall cost by aggregating the initial cost of the facade assembly with long-term operational costs, e.g., 10 years of energy costs. Carbon optimization, LCA. For true environmental performance, optimization often includes calculating the lowest total kilogram, CO2 emissions. This involves combining the embedded carbon in the materials, life cycle assessment, or LCA, with the carbon emissions generated by the building's operational energy use. Kinetic and responsive envelopes. The methodology is essential for developing complex kinetic building envelopes that are designed to be interactive and responsive to external natural energy sources like solar radiation and seasonal wind, thus creating an acclimated building that intelligently reduces HVAC system energy consumption. A significant challenge addressed by parametric optimization is ensuring the envelope remains high-performing even as external conditions change. An envelope solution optimized only for current conditions will not remain optimal over time, particularly as global warming may expand the length of the shading period required. Parametric methodology incorporates this by allowing the designer to predict and incorporate likely changes to external influences into the optimization model, e.g., climate predictions for 2020 to 2080 scenarios, which yields better long-term results than a design optimized solely for current conditions. The application of parametric design to climate-responsive architecture fundamentally aims to optimize buildings for energy efficiency and environmental compatibility by automating complex evaluation processes. Parametric tools allow rapid prototyping with performance feedback by enabling designers to simultaneously evaluate a wide range of alternative solutions and use quick analyses for real-time design decisions. This capability is achieved by linking parametrically controlled geometry to energy simulation tools and optimization algorithms. Furthermore, this methodology ensures that data integration ensures function follows form through performance-based generative design, where environmental and functional criteria, such as minimizing cooling load or maximizing daylight, or transcoded into geometric differentiation, driving the generation of the building's optimal shape and envelope rather than resulting from prior decisions. This process is most effective when used early, as decisions made in the conceptual design phase have the greatest impact on a building's overall performance, and is inherently iterative as it requires the generation and testing of multiple solutions, promoting collaborative workflows by providing tools that streamline processes and encourage interdisciplinary information exchange across the project lifecycle.